Hello everybody, welcome to the second part of our course, which is our vectors and scalars section of the course. For those of you who've taken physics, you'll have some ideas about what a vector and a scalar are, but we are going to take a different look at them in calculus here. We're going to look at how we use them algebraically. The intro, the first few lessons will maybe seem the same, but then we'll start to look at them in a different way. So first, just for those that are unaware, a quick review for those of you who've seen this before, the difference between what we call a vector measurement and a scalar measurement. So a vector is any quantity that has both a magnitude and a direction, and a scalar is a quantity that has just magnitude. So some common examples that we see is that we have a scalar that is called speed, which has a magnitude. Magnitude just means size or a measurement. So for example, we are going 60 kilometers per hour would be a speed. Its vector partner then would be what we call velocity. So velocity would have the magnitude piece, 60 kilometers per hour, but a vector then also adds on direction. And we usually put that in square brackets afterwards. So I'll say 60 kilometers per hour north. So this vector quantity has both a magnitude and it has a direction. Another common example that we can use would be a scalar called distance, something like say 100 meters, and its vector partner called displacement, which would then have its magnitude and would have a direction, say for example north 30 degrees east. So one of the homework questions is going to ask you to tell the difference between some measurements. So really what you're looking at is, does a certain measurement have a magnitude only, or does that measurement have both a magnitude and a direction that would go with that? To represent a vector then, in the next part here, we use what is called a directed line segment, okay, which really just means we're going to draw a line, but to indicate direction, we put an arrow on the end. And like we've done before with a line segment, we can put then points on the end, points A and B. The difference here is if it was just points A and B, we would have, say, a scalar, because I've now added this arrow on here indicating that we are going from A to B. We've added in that direction piece, so we would now call this a vector. We would still have then A being our start or initial point, and we would have B as the end or the terminal point. Sometimes this end, when we're talking about a vector, is referred to as the tail. And this end up here is referred to as the head or the tip of the vector. Think of it kind of like a dog, the back end, the tail, the front end, the head. Notation that we use. So in past, if I wanted to refer to a line segment, I would simply just say I have a line segment AB. Because we're now adding direction to this, we add this direction bar over top, which is our vector symbol. So I would now read this as vector AB. And this is referred to as a point-to-point vector. We can also give this line segment, or in this case now a vector, a name. As we would in previous years, drawing triangles, we may call a line segment by variable. Now that this is a vector, we do the same thing. We just put this vector bar over top of it. So I could also call this then vector A. To represent magnitude, when we're drawing these line segments or these directed line segments, really what we're looking at then is what is the length of that line segment would be the magnitude piece. And to represent that in notation, what we do is we actually write absolute value bars on both sides of the vector. So when you see a vector with the absolute value bars, it means we're talking about what is the magnitude of that vector. And likewise, we can do that with this notation here as well. And then our direction, as we saw up here, we usually just use square brackets. after the magnitude. In this case, it looks like roughly that direction maybe would be something like northeast. So for our example, I'll write that in there. When we look at vectors, we have different types of vectors that we're going to explain here in just a second. To do that, I'm going to use this as my example. So I'm just saying, let's assume that we have these 5 points, A, B, C, D, and E, that are all equally spaced along this line, and we'll say that they are all 1 unit apart. So this is 1 unit away from this, and so on and so on. The first type of vectors that we can have then is, what does it mean for two vectors to be equal? So two vectors are equal if and only if they have the same magnitude and the same direction. So vectors need to have both pieces to be the same for them to be equal. So for example, if I created vector A, B on this line segment, this is saying vector from A to B, we're going to the right and it's 1 unit long. Any vector on here then that is going to the right that is 1 unit long would be equal to AB. So AB would be equal to, say, BC, which is then also equal to CD, which is also then equal to DE. These would all be considered equal vectors. We could also say then a vector like AC, still going to the right, but now 2 units long. So I could set that equal to any vector that is going to the right that is 2 units long, for instance, BD. We can switch the direction around. I could say, what if we have vector EB? Now, the order of the letters is important. EB means we're starting at E and we're ending at B, like we did here, our start and our terminal point. So if I'm going from E to B, means we are going to the left. And this has to be 3 units long, so this could be then equivalent to, say, vector DA, which is also going to the left and is 3 units long. Opposite vectors are any two vectors that have the same magnitude but are pointing in the opposite direction. In other words, vector AB, which is 1 unit long pointing to the right, is opposite to well, I could use the exact same letters, but just point it to the left. So that would be opposite to BA. Or we could pick any vector that has the same magnitude, which is 1 unit long, that is now pointing to the left. So BA points to the left. We could also say here DC is also opposite here because it is 1 unit long, pointing to the left. Likewise, we could do, say, DB, which is a vector pointing to the left that is 2 units long. We could say is opposite to then vector, I just need a vector that is 2 units long that's pointing to the right. So it would be opposite to, say, something like AC. When we see that we have the negative of vector, it means that it must have the same magnitude but pointing in the opposite direction. For instance, if I look at negative AB, it means that this vector here, the negative of AB, has to have the same magnitude as AB, which is 1 unit long, but it has to be pointing in the opposite direction. That's what this negative means. In other words, negative AB would be equivalent to BA. Since AB points to the right, the negative of AB must point to the left, and they have to have the same length. If I said the negative of EC, E to C is 2 units long, pointing to the left, so the negative of this must be then 2 units long and pointing to the right. So for instance, CE would be then equivalent to the negative of EC. And what we should see here is that when we have the negative of a vector, all we have to do is just switch the points. To make that vector positive. Parallel vectors, so any two vectors that have the same or the opposite direction. In this case, then, all of these vectors that we're creating on this line segment would either have the same or the opposite direction. So we could create any number of parallel vectors here. Note that the magnitude does not need to be the same for them to be parallel. And we're going to start to use this word, what we call scalar multiples, here as well. So the idea here is that AB, okay, vector AB, would be parallel to vector BD. They have the same direction. The fact that they don't have the same magnitude does not matter. The idea here, though, that we get when we start talking about this idea of them being scalar multiples is that if I look at vector BD, BD is 2 units long, I could say that BD is equivalent to 2 of AB. I could also say BC is parallel to DB. BC, here it is, from B to C is parallel to D to B. They are parallel because they are opposite in direction. As scalar multiples, though, we could say here that DB is equal to, so to get to from D to B, how could I write that using BC? Well, because they're in opposite directions, we saw this idea up here, we can say that it must be the negative of 2BC. So to get from D to B, I need the opposite direction of BC, and I need 2 of them. So the opposite direction, and I need 2 of them to get these to be equivalent. And this is the idea where we call these scalar multiples. In other words, one vector is some scalar. A scalar is just a number, remember from up here, is just some number multiplied by the other vector. Lastly, if we do one more, I could say here that AC is parallel to AE. So far we've always been writing the bigger vector first. We don't have to. We could say then AC is what multiple of AE. So AC is what multiple of AE, and hopefully from the line segment we would see that we need half of AE for these to be equivalent. So half of AE is the same as AC. They're pointing in the same direction, so we don't need the negative. We're only comparing their magnitude at that point. Lastly, we have what we call a unit vector. Unit vectors are any vector that has a magnitude of length 1. So for example, any of these vectors here, such as say AB would be a unit vector since its length is only 1 unit long. If we use our other notation, you'll see that instead of writing a little arrow on top, what we write here instead is what we call a caret. And that tells us that that vector is only 1 unit long. And lastly, any vector can be made into a unit vector by dividing by its magnitude. So for example, to demonstrate this, I'll say let vector M be equivalent to AC. And if we go to our diagram, we see that AC is 2 units long. If I want to create a unit vector, then I would say then unit vector M, and that's how we would read this. Okay, so this is vector M, this is unit vector M. To make this into a unit vector, what I would see is that since AC is 2 units long, then to make a unit vector, I would have to multiply that by its magnitude, which is 2 units. So if I take vector M and I multiply it by a half, I would get unit vector M. In general, we can say then any vector A can be turned into a unit vector A if I just multiply by whatever that magnitude is. So take vector A and multiply it by 1 over its magnitude, and that will create a unit vector just as we did here. Lastly, I have here 0 vector. I can't demonstrate that on our diagram very easily, but a 0 vector is just any vector that has a magnitude of 0 and its direction is undefined. It doesn't necessarily make a whole lot of sense when we're talking about trying to represent something like this here, but in terms of doing some algebra, it's important that we have that vector defined. Lastly, then a couple examples here that we can look through to make these ideas hopefully a little bit more clear. So in this first example, I'm going to give you vectors A, B, and C. I'm going to tell you a little bit about them. One, they are all parallel. That means they're either pointing in the same or opposite direction. The absolute value bars is telling you the magnitude. So the first vector has a magnitude of 1, second magnitude 2, and the third has a magnitude of 4. And lastly, I'm going to tell you that A and B specifically are pointing in the same direction, and then vector C is pointing in the opposite direction. So part A says, well, let's make a quick sketch then of what these vectors are looking like. So my quick sketch is just going to be like this. I'm going to say, okay, the first one I'm going to draw to be about 1 centimeter long. I'm going to call that vector A. The second one then, vector B, has to be twice as long. It has a magnitude of 2. So I'm going to say there is vector B. Okay, pointing in the same direction. They are parallel to each other with the same direction. And then lastly, I need a vector C, which now has to be 4 units long. So there it is. And this one we need to be careful because it has to point in the opposite direction. So now I'm going to put the arrow on this end and say there is vector C. Second part then says to write each vector as a scalar multiple of the other two vectors. In other words, vector A is equivalent to, well, how could I write that as a multiple of B? And what we should hopefully see here is that A is half as big as B. So vector A is then half of vector B. If I look at C, two things should be happening here. One, this is 1/4 of the length of C, but they're pointing in opposite directions. So A is equivalent to then the negative, the opposite direction, and it's 1/4 as big as C. So A is negative 1/4 of C. The negative changes its direction, and it's 1/4 as big. We can do this with B then as well. Vector B is equal to, what can I do to A to make these equivalent? I would need 2 of A to make them the same. And if I compare that to vector C, again, we need to change its direction, so that needs to be negative. And if we see here that how much of C do I need, we would need to multiply C by 1/2. So vector B is in the opposite direction, and it's half as big as C. Lastly, if I start with C, okay, how can I make C and A equivalent? Again, I need A to point in the other direction, so they would point the same way as C. So I need to make this negative. I need the negative of A, and I need it to be 4 times bigger. So C is equivalent to the negative 4 of A. And lastly, compare it to B. Again, we need to change its direction, and I would need 2 of vector B for these to be equivalent. And then our last example here, I've given you a vector, and this is where we're heading when we talk about algebraic vectors. We actually represent vectors often on our Cartesian plane. So as we move along, this is where we're going to head to, is how do I represent vectors on our Cartesian plane? So we're seeing it here for the first time. We do have its starting point, or its tail, and we have its tip, or its head, okay, located at key points on our Cartesian plane. The question is asking us then, what's the magnitude in the direction of A? In our direction, we're going to define that relative to the positive x direction. So how long is it? And then what direction are we pointing? And we're going to tell us this relative to that positive x direction. So if I want the magnitude on here, what I can do is put in a right triangle. And now we can use Pythagorean theorem. So this is 4 units long, and this side is 3 units long. So using Pythagorean theorem, what we would see is that the magnitude of A, so again, we see these absolute value bars. At this point, I'm not talking about just the vector, but specifically just its magnitude. How long is that line segment? So the magnitude of vector A squared must equal 4 squared plus 3 squared from Pythagorean theorem. We would have then the absolute value of A equals, okay, we can treat this just like we would any other variable as we are solving. Getting rid of that square is square root. If I square these and add them up, we would get 25. In other words, the magnitude of vector A is 5. The length of that line segment is 5 units long. And we did that back in grade 10 when we did our length of a line segment in our second unit. The piece that we're adding on, though, is now that this is a vector, I also need a direction. So here is my positive x direction right here. So what I'm looking for then is relative to that, what is that angle? So I'm going to call that angle theta. And now we can use a little bit of trigonometry here. In a right triangle, we have our opposite and adjacent side. So I can use our tan ratio. Tan of theta is equal to 3 over 4. Quick reminder here as we solve then, tan inverse of 3/4. And if we do this on our calculator, we should find that this is approximately 37 degrees. So then we can put these two measurements together to create the vector. Vector A is equal to 5 units, and our direction in square brackets afterwards, I'm going to say here 37 degrees from positive x direction. Using some shorthand here just to try and make it a little bit shorter. We will have to be careful in some of your homework questions because on the Cartesian plane you might have vectors that are pointing in this direction here. So as you complete this right triangle, you'll have something like this here. That won't stop you from being able to find the magnitude, but you're going to have to be careful. As we go to find that direction, I'm going to have this angle here, but if we're stating it relative to the positive x direction, it's this angle here you're going to need. So a reminder that if I know how big theta is, then I can get this angle here by doing 180 degrees minus theta. So we can still solve for this the same way we did here. The only difference is now I'm going to use this to figure out that angle that will tell me relative to the positive x direction. Hope the video helps. So let me know if you have any questions. Okay, I'll post a copy of the notes so you can read through it, and then some questions for you to try. Have a good day, guys.